Ladies and gentlemen, welcome to the next module of the Introductions to Programming. In this module, I introduce you to cellular automata. First, let us briefly consider the basic definition of a cellular automata, or in short, a CA. It consists of the following elements: an arrangement of cells, which can be a row or a grid, that defines the topology of the cells, so which cells are neighboring to which others. Each of the cells in the automata can have a state. In the simplest case, this is either 0 or 1, or on or off, or dead or alive. So these are different ideas how we call the state of a cell. And a definition which cell or which cells are the neighbors of a cell that we consider. This can be the direct neighbors or a wider area, so we are completely free in this definition. And finally, there is a set of rules, a transition rule or transition rules that define how a cell changes its state. So how, for example, it changes from 0 to 1, from dead to alive. And this change is usually based on the definition of the neighbors and the status of the neighbors that we have defined. So how many alive cells we find in our neighborhood, for example, defines how a cell that I consider changes its state. In general, there are one-dimensional cellular automata, which is a row of cells, and in this row we can define the neighbor of a cell by its left and its right neighbor, or the two left and two right neighbors, and so on and so on. And based on this status of the neighbors, we define how I change the status of a cell in the next step, in the next iteration of the automata. Often the different states or different iterations of this automata is visualized in one row after the others, which creates a kind of a two-dimensional pattern. But this 2D pattern results from the iterative development of a one-dimensional automata. In our examples in the following, we consider primarily two-dimensional automata, respectively three-dimensional automata, since they are closer to architectural applications, at least from my point of view. Whereas there are also examples of facades that are inspired by one-dimensional cellular automata, which you can see in the image. There is also a lot of theory behind CA. There are a lot of examples and also general introductions, how to understand it, how to use it, how to program it. A few links to this background information I provide you below this video in the text for your self-study. Now let's consider the basic setup of a cellular automata. We will use a regular grid of squares or rectangles, and we start also from a two-dimensional grid. But, as I mentioned, you can also change this topology. You can use hexagonals, and you can also use a Voronoi diagram, where it becomes a little bit more complicated because the number of neighboring cells is not constant. But for the introduction of the technique and the method of CA, we start with a regular grid. The most often neighbors or neighborhoods or used by a CA, it's the so-called Moore neighborhood, which is the 8 directly neighboring cells around a considered cell. So you can see an illustration on the slide. The other neighborhood that is very prominent is the von Neumann neighborhood, which is the 4 directly connected cells to the right, the left, the top and the bottom to a considered cell. These neighborhoods that I define, they are also called the voting rule of a CA. The heart of a CA are its transition rules. They define how a cell changes its state from one to another. These rules are called the counting rules, since the transition depends on how many dead or alive cells we can count in the neighborhood that we've defined before. We use in our examples the following rules. If a cell has the state 1, or if it's alive or active, then the first rule is how many cells we need at least so that the cell can remain in the state 1, so that it can keep being alive. The second rule for a cell that have the state 1 is how many rules a cell can have in the maximum in before it dies by overcrowded neighborhood, so to say. And means if we have more than this defined number of active neighboring cells, the cell changes its state from 1 to 0. The third rule applies to cells that have the cell at the state 0. And this says how many cells a dead cell should have around itself so that it becomes alive again, so that it changes its state from 0 to 1. And the fourth rule defines how many cells it can have in a maximum to be reborn. So these last two rules define the domain, the area of values in between which a cell changes its state from 0 to 1. We will see examples that illustrates these rules in the following, and these are something we will work a lot to explore the dynamics and the behavior of the cellular automata, because that's really the key idea of the CA, to explore these rules in combination with the neighborhood, of course, to control the local changes or the changes of the cell based on the local conditions in our universe, which is the grid that we created. So this grid can be very small, from let's say 10 by 10 cells, and it can be extremely huge with thousands of cells in the grid. The transition rules applies always on the local neighborhood only, and the neighborhood is the neighborhood that we defined. So responsible for the huge diversity in the universe of cellular automata is especially the really huge amount of possible rules that we can define for these transitions. The formal notation of these rules, at least in our simple case, is written by 4 numbers. For example, it's 4, 5, 5, 5, or some other combination of 4 numbers, which defines the values for the rules that I've described in before. Okay, so in the examples that we consider in the following, I provide you these examples really to inspire you and to generate your own architectural experiments, to generate configurations for facades, or for building configurations, or even for urban fabric, that you can generate complex structures by applying 2 and 3D cellular automata. As always with these introductions, I can only show you the first steps in the topic. I hope you will enjoy exploring the potentials of cellular automata and creating your own applications out of it.